Let's talk about a hidden world that's constantly at work all around us, in our cars, our phones, and even in the medical devices that save lives. It's a world of invisible forces and the tiny, brilliant gadgets that measure them, pressure sensors. So, what's the secret connection between the phone in your pocket, the engine under your car's hood, and the ventilator helping someone breathe in a hospital? Well, as you might have guessed, it's the unsung hero of modern technology, the pressure sensor. So here's our game plan. We'll start with the absolute basics, what pressure even is. Then we'll look at the different ways it's measured. After that, we're going to dive into the really cool mechanics of how these sensors actually work. And finally, we'll see how engineers figure out which sensor is the right one for the right job. Okay, first things first. Before we can get into the sensors, we've got to understand the fundamental force they're designed to measure. Let's talk about pressure. At its very core, pressure is just force divided by area. A great way to think about this is to imagine pushing on a wall. If you use your whole palm, the pressure is pretty low. But if you use that exact same force with just your fingertip, the pressure is huge. Same force, different area, totally different pressure. This simple idea is the key to everything else we're going to talk about. Now here's where it gets really interesting. Measuring pressure isn't always as simple as it sounds because it completely depends on what you're measuring it against. Your starting point or your reference is absolutely key. This diagram here breaks it down beautifully. So first, look at that blue arrow for absolute pressure. Its baseline is 0, a perfect vacuum, nothing. Then the red arrow shows you gauge pressure. This is what you're measuring when you check your tire pressure. It's always relative to the atmospheric pressure all around us. And finally, those orange arrows show differential pressure, which is simply the difference between any 2 points. Okay, so how do we actually turn that physical push, that force, into an electrical signal we can use? Well, one of the most common ways is by measuring tiny changes in electrical resistance. Let's start with piezoresistive sensors. Now, the name sounds super technical, but it actually tells you exactly what it does. Piezo comes from the Greek word meaning to squeeze, and resistive is, well, electrical resistance. So these are literally sensors whose resistance changes when you squeeze or stretch them. Here's a look at how it works. You see that thin circular part? That's a diaphragm. When pressure from the outside pushes on it, it flexes, just a little bit. This bending action creates mechanical stress on those tiny resistors that are built right onto its surface. And that stress changes how easily electricity can flow through them. Now let's see how this all comes together. The image on the left, that's a microscopic view of the 4 resistors placed just so on the diaphragm. Then on the right, you see how they're wired up into what's called a Wheatstone bridge. You can think of this circuit as a super sensitive balancing scale for electricity. When pressure causes even a tiny change in one of those resistors, it knocks the whole bridge out of balance, and that creates a signal we can measure. So to wrap it all up, it's a perfect little chain reaction. Pressure bends the diaphragm. The bend creates strain. The strain changes the resistance, and the Wheatstone bridge turns that change into a usable voltage. It's simple, it's elegant, and it's incredibly effective. Now, a very similar idea is at the heart of strain gauge sensors, but instead of tiny resistors embedded into the material, these use a foil or wire gauge that's bonded right onto a metal diaphragm. And the process here is almost identical. Pressure pushes on the diaphragm, which physically stretches or squishes the strain gauge attached to it. That deformation changes its resistance, and, you guessed it, a Wheatstone bridge circuit turns that tiny change into a really precise electrical signal. Okay, so we've talked about resistance, but that's not the only electrical trick in the book. Let's look at a couple of other clever ways to measure pressure, using things like capacitance and electric charge. Capacitive sensors use a totally different property, the ability to store an electric charge, which is called capacitance. The principle is actually really simple. Just imagine 2 metal plates. The closer they get to each other without actually touching, the more charge they can store between them. And this diagram shows you exactly how that becomes a sensor. You've got one plate that's fixed and a flexible diaphragm that acts as the second plate. When pressure is applied, it pushes that diaphragm closer to the fixed plate, shrinking the gap and, you guessed it, changing the capacitance. So the whole process is beautifully direct. The diaphragm moves, the distance shrinks, the capacitance goes up, and a circuit translates that increase into a precise pressure reading. This method is fantastic for measuring very, very low pressures. Next up, we have something that feels a little bit like magic, the piezoelectric effect. Certain materials, like quartz crystals, have this amazing property. When you squeeze them, they actually generate their own electric charge. You don't even need to power the sensing part itself. And here it is in action. Pressure on the diaphragm squeezes a crystal inside. As that crystal deforms, it generates its own voltage, and that voltage is directly proportional to the force. It's this self-generating power that makes these sensors absolutely perfect for measuring dynamic, fast-changing events, like the powerful, split-second explosions inside an engine's cylinder. So, we've seen 4 different technologies, and each one is brilliant in its own way. So how do you pick the right one? Well, it all comes down to matching the sensor's strengths and weaknesses to the very specific job it needs to do. This table really lays out all the trade-offs. Need something really sensitive in a tiny package? A piezo-resistive sensor is a great bet, but you have to be careful about temperature changes. Measuring very low, steady pressure? Capacitive is your best choice, but you need to protect it from electrical noise. Trying to capture a rapid, dynamic event? Piezoelectric is the undisputed champion, but it can't measure a constant, static pressure. And if you need the absolute highest accuracy, a strain gauge is perfect, but it needs some extra electronics. It just goes to show, there's no single best sensor, only the best fit for the task. And these applications are absolutely everywhere. We're talking about making sure your car's tires are inflated correctly, keeping industrial pipelines safe, helping a patient breathe with a ventilator, or even telling a pilot their altitude. These sensors are truly the invisible nervous system of our modern world. And all of this brings us to a final thought. We've seen how critical these sensors already are, but as we move toward a future with smarter cities, more autonomous vehicles, and increasingly personalized medicine, where is the next big need for these tiny, powerful devices going to pop up? That's a question that engineers are trying to answer every single day.